What if I told you that the barista who served your coffee this morning has witnessed the collapse of civilization? What if your college professor knows exactly when humanity will make contact with extraterrestrial life? What if the quiet person sitting in the back of the bus has seen your death, your birth, and everything in between? Right now, as you're watching this video, there might be someone from the year 2087 standing behind you, taking notes on this exact moment in history. Sound impossible? By the end of this video, you'll question everything you think you know about time, reality, and the people around you. Because the evidence I'm about to show you suggests that time travelers aren't coming. They're already here. They've always been here. And they're hiding in plain sight. Some of them might even be watching this video right now, from a future where the lazy cosmos has become the most important channel in human history. But we're getting ahead of ourselves, aren't we? Or maybe we're getting behind ourselves. When you're dealing with time travel, those distinctions start to matter a lot less than you'd think. We now shift our focus from mystery to method, diving deep into the scientific backbone that supports time travel's tantalizing potential. This is not idle speculation or the stuff of mere science fiction. These are theories, equations, and paradoxes that have rigorously occupied the minds of the greatest physicists for over a century. Welcome to the heart of our inquiry, the science of time travel. It all begins, as so much of modern physics does, with Albert Einstein. In 1905, Einstein introduced his special theory of relativity, shattering the classical Newtonian view that time was an absolute, unchanging backdrop to the universe's drama. For Newton, time flows equably without relation to anything external. But Einstein realized that time, like space, was relative, subject to the observer's frame of reference. Einstein's breakthrough was motivated by the dilemma posed by light. Classical physics had no good explanation for how the speed of light could remain constant for every observer, regardless of their movement. But in Einstein's universe, time itself would flex to ensure the constancy of light speed. Imagine two twins, Alice and Bob. Alice stays here on Earth, while Bob sets off for a journey near the speed of light. When Bob returns, he'll discover that Alice has aged far more than he has. This is the twin paradox, a thought experiment that reveals the power of time dilation. Time slows down for those moving rapidly relative to others. You might be wondering, is this just theoretical? Far from it. Every time you use GPS navigation in your car or phone, you're relying on satellites whose clocks must be adjusted for time dilation, both from velocity and from the curvature of space-time caused by Earth's gravity. Without these corrections, your location would be off by kilometers every single day. This isn't fiction. These are the practical consequences of Einstein's equations. Similarly, in particle accelerators like those at CERN, muons are created that, according to classical physics, should decay almost instantly. Yet they persist for far longer, because they're moving so rapidly that from our stationary perspective, their internal clocks are ticking much slower. These real-world effects are undeniable evidence that time can be manipulated by speed and gravity. But as astounding as special relativity is, it's Einstein's general theory, published in 1915, that truly opens the door to time travel's extraordinary possibilities. General relativity treats gravity not as a force, but as the curvature of space-time caused by massive objects. Space and time are stitched together into a single, four-dimensional fabric. Every planet, star, and black hole bends this fabric, altering the flow of time around them. Time passes more slowly closer to massive objects, a phenomenon confirmed by atomic clocks flown in airplanes or placed at different elevations on Earth. Here's where time travel becomes more than idle daydreaming. If space-time can be bent, twisted, and folded, could it be manipulated to allow actual transportation into the past or future? Physicists call this the search for closed time-like curves, paths through space-time that loop back on themselves, returning a traveler to their own past. It may sound like paradoxical magic, but it emerges naturally from Einstein's equations under extreme conditions. One of the earliest post-Einstein attempts to grapple with time travel came from Kurt Gödel, the mathematician famous for his incompleteness theorems. In 1949, Gödel discovered a solution to Einstein's field equations describing a rotating universe, one where closed time-like curves would be inevitable. In other words, in a universe that rotated fast enough, it would be possible for a spaceship to set off and, by following a precise trajectory, return to its own past. Realistically, our universe doesn't spin nearly fast enough, but Gödel's work established that backward time travel was not forbidden by the laws of nature. This opened the floodgates for physicists to search for other possible ways to breach time's apparent barriers. Let's examine the most prominent theoretical models. Wormholes. Einstein-Rosen bridges. In 1935, Einstein and Nathan Rosen described bridges in the fabric of spacetime connecting two distant points. These Einstein-Rosen bridges, later dubbed wormholes, are shortcuts through spacetime that could, in principle, link not just distant places, but distant times. A wormhole is not a tunnel through space. It's a tunnel through spacetime itself. Imagine creating a wormhole and then moving one end at near light speed, or placing it close to a massive object where time slows down. The two mouths of the wormhole would experience time differently due to relativistic effects. Step through one mouth, and you might emerge from the other at a point in the past or future. Kip Thorne, one of the leading experts on gravitational physics, explored these scenarios in the 1980s, showing that if traversable wormholes could exist and be stabilized by exotic matter, stuff with negative energy density, they could be used as time machines. Of course, stabilizing a wormhole, let alone creating one, is beyond our current technology. The universe has not yielded any evidence of naturally occurring traversable wormholes, and exotic matter remains entirely theoretical. Nonetheless, the mathematics remain sound, and the principle is a foundation stone in the scientific study of time travel. Closed, time-like curves, and rotating black holes. Another theoretical route revolves around black holes, especially rotating, or Kerr, black holes. In 1963, Roy Kerr described solutions to Einstein's equations showing that a rotating black hole drags space-time around with it in a process called frame dragging. Some solutions imply the existence of regions where closed time-like curves could form, paths that loop back through time. Frank Tipler advanced the idea by considering a long, infinitely dense rotating cylinder, sometimes called a Tipler cylinder. If such a structure existed and spun rapidly enough, it could twist space-time so much that traveling along certain paths around it would bring an observer back to their own past. However, these models require conditions far removed from practical reality. Tipler's cylinder would need to be infinitely long. Kerr black holes must be perfectly stable and empty of infalling matter. Still, each of these theoretical constructs demonstrates that time travel isn't strictly forbidden by the fundamental laws of physics. Quantum mechanics and time travel. No discussion of time travel would be complete without visiting the wild landscape of quantum mechanics. While relativity deals with the cosmic scale of space-time's curvature, quantum physics explores the universe at the smallest scales. Remarkably, the implications for time travel are no less profound. One of the stranger predictions of quantum mechanics is quantum tunneling. Sometimes, a particle leaps across a barrier that should stop it, seemingly vanishing from one place and reappearing in another without traversing the intervening space in a classical way. Some experiments have suggested these transitions occur faster than light could travel, raising questions about whether information, or, in some sense, particles themselves, can travel backward in time. While these effects don't allow for macroscopic time travel, they hint at cracks in the surface of reality where causality blurs and the arrow of time is not as rigid as we imagine. Even more provocative is the delayed choice quantum eraser experiment. Richard Feynman, perhaps the most famous quantum physicist after Einstein, described all of quantum theory as nature's way of not letting us know what she's up to. In delayed choice experiments, the act of measuring a particle seems to retroactively decide its history, changing the outcome of events that by classical reasoning have already occurred. While this is not the same as traveling backward in time, it reveals a universe where causality is malleable and information can traverse time in ways forbidden to matter. Venturing further into quantum territory, we encounter the many worlds interpretation. Proposed by Hugh Everett in 1957, this theory posits that every quantum event splits the universe into multiple coexisting realities, each with its own history and future. In this framework, the paradoxes of time travel, like killing one's grandfather before one's parent is born, are resolved. The act of traveling to the past and making changes simply creates a new parallel universe in which those changes unfold. Your original timeline goes unaffected, while the new timeline encompasses the consequences of your actions. A neat solution to the notorious paradoxes of time travel. The paradoxes of time travel. Speaking of paradoxes, the most famous is the grandfather paradox. What happens if you travel to the past and do something that prevents your own existence? This problem has troubled philosophers and physicists for decades. One attempted solution is the Novikov self-consistency principle, formulated by Igor Novikov in 1980. This principle proposes that the only events that can occur along closed timelike curves are those that remain self-consistent. The timeline cannot be altered in a way that generates a logical contradiction. In other words, no matter how hard you try, something will always intervene to prevent paradoxical outcomes. If you attempt to kill your grandfather in the past, you will fail, not because of fate, but because the fundamental fabric of space-time enforces consistency. This principle is supported in part by solutions to Einstein's equations. When physicists model situations involving time travel, they find that, at least in theory, only self-consistent sequences of events can occur. It's as if the universe defends itself against paradox, channeling causality into closed loops of events compatible with its own logic. At this point, a natural question arises. If time travel is permitted by the laws of physics, and paradoxes can be skirted by self-consistency or parallel worlds, Why don't we see time travelers everywhere? Physicist Stephen Hawking approached this question with characteristic wit, proposing the chronology protection conjecture. Hawking speculated that quantum effects around would-be time machines might always conspire to destroy them or prevent their use. In other words, the universe has a built-in protection against the chaos of time travel. The rules of quantum physics shut the door just as you're about to step through. His calculations showed that attempting to create a time machine by warping space-time could result in catastrophic energy feedback, destroying the time machine before it could function. Nonetheless, Hawking also famously held a party for time travelers in 2009, publicizing the event only after it happened, as a tongue-in-cheek attempt to attract visitors from the future. No one attended, but the point was to illustrate both the strange logic and the challenges inherent in testing the possibility of time travel. Contemporary experimental frontiers. Where, then, does the current frontier of time travel research reside? The Large Hadron Collider, LHC, at CERN, is humanity's most powerful physics laboratory, capable of smashing subatomic particles together at energy levels unseen since the universe's creation. Some theoretical models suggest that at these energies, tiny black holes, or even micro wormholes, might form, persisting for incredibly short periods. While no evidence for wormholes has been detected, researchers are actively studying whether the behavior of particles at these energies hints at new dimensions, alternate paths through spacetime, or perhaps clues to the quantum structure of time itself. In 2014, physicists studied the possibility that the Higgs boson, the particle responsible for mass, might influence the structure of spacetime in subtle ways, affecting how future and past interact at the quantum level. Elsewhere, scientists are exploring time crystals, a newly discovered phase of matter that, in essence, oscillate perpetually in time without using energy. While these are a far cry from a time machine, their existence suggests that the universe harbors unexpected properties related to the flow and manipulation of time, waiting to be uncovered. Warp drives and faster-than-light travel. An oft-cited route to time travel involves the hypothetical warp drive, a concept made famous by Miguel Alcubierre in 1994. Alcubierre's metric exploits Einstein's equations to compress space-time ahead of a vehicle and expand it behind, allowing the vehicle to move faster than the speed of light relative to distant observers, but without locally violating the law that says nothing can move faster than light. The catch is that such a drive would require vast quantities of negative energy, a technology utterly beyond current capabilities. But if it could be built, relativity predicts that faster-than-light travel can lead to backward time travel, at least in some frames of reference. The implications here are staggering. If warp drives are ever built, time travel follows almost as an unavoidable consequence. Time travel in the lab. A fascinating area of research involves temporal non-locality, where particles become entangled not just across space, but across time. Experiments have demonstrated that photons can be entangled such that measuring one can instantaneously affect the other, even if they're separated by years, not just by kilometers. Here, information leaps across time, albeit only at the quantum level. Another hint, perhaps, that time's arrow is not as rigid as it seems. In 2013, physicist Robert Nemiroff and Teresa Wilson mounted a very public search for time travelers online, scouring social media and forums for specific predictive information posted before key events. Though the search yielded no concrete results, the methodology highlighted how our increasingly digital world might allow us to spot temporal anomalies, if they exist, more easily than ever before. Philosophical and logical boundaries. Though much of our discussion thus far has centered on equations and experiments, the philosophical implications of time travel are just as striking. For centuries, thinkers have pondered the nature of the past, present, and future. Augustinian theology, Buddhist teachings, and the writings of Gödel and Wittgenstein each grapple with the fluid boundaries of time, questioning whether the future is as real as the past, or whether our experience of time is merely a psychological construct. Modern physics leans toward the block universe view, where past, present, and future all exist simultaneously in space-time, differentiated only by our point of view. Time travel, in this context, is not a violation of physics, but simply a movement through an unchanging, eternal structure. The challenge for science is not whether time can be traversed, but how the machinery of the universe might facilitate or frustrate such journeys. Future directions. Experimental and observational tests. What does the future hold for time travel research? Advances in quantum computing, ultra-precise atomic clocks, and the study of gravitational waves are pushing the boundaries of our understanding. The era of quantum gravity, a theory that unifies general relativity's account of space-time with the probabilistic tapestry of quantum mechanics, may yield entirely new possibilities for manipulating time at both subatomic and cosmic scales. Some researchers, including those at the Perimeter Institute in Canada and the Institute for Advanced Study in the United States, are actively refining theories of causal sets, a radical reimagining of space-time where events are discrete, like dots on a grid, rather than continuous, smoothly flowing entities. If this view is correct, then time travel might one day be possible by hopping from one allowed event to another, leaping across the chains of causality as easily as traversing space. Others are searching for evidence of time travel by observing the behavior of fundamental particles for deviations from expectation. A hint, perhaps, that travelers from other timelines or epochs have subtly impacted our universe. The search is ongoing and limited only by human imagination, ingenuity, and perhaps the mysterious defense mechanisms embedded in the laws of nature. Summary: where science stands on time travel. Let's sum up. Einstein revealed that time is not absolute. It flexes, stretches, and compresses based on speed and gravity. General relativity's equations permit exotic structures: wormholes, rotating black holes, spinning cylinders, that under extreme conditions could create loops in time. Quantum mechanics shows us that at the smallest scales, causality itself is not sacred, allowing for information to traverse time or events to be retroactively decided. The most famous paradoxes of time travel, the grandfather paradox, bootstrap paradoxes, can be resolved either by embracing parallel universes or by enforcing self-consistency, where contradictions simply cannot be enacted. Despite these extraordinary theoretical possibilities, practical time travel remains elusive. No one has observed a physical wormhole, measured evidence of a time traveler, or encountered incontrovertible proof that causality has been tampered with on a macroscopic scale. But every year, experimental physics edges closer to the kinds of energies, measurement precision, and theoretical insights needed to push these questions further. Why does science explore time travel, this tantalizing yet treacherous terrain? Because the implications reach not just to questions of transportation, but to the heart of existence. If time can be traversed, influenced, or rewritten, our very concepts of causality, identity, and morality must be reconsidered. We must contemplate not just who we are, but when we are, and whether our story is a fixed line stretching from birth to death, or an intricate tapestry woven from countless possible threads. As we move forward in this investigation, keep in mind that the universe is not a static theater, but a dynamic, living story. Time may prove to be just as flexible, surprising, and susceptible to our ingenuity as space already has. Next, we will step beyond equations and thought experiments to examine the puzzling historical evidence. Those moments when the impossible seemed to flicker briefly into reality, when future knowledge appeared in the past, and when individuals, technologies, or even objects seemed to leap across time's divide. But for now, let it sink in. The science of time travel is very much real, alive, and growing, guided by mathematical rigor and relentless curiosity. If humanity ever discovers how to traverse time, the journey will have begun with the equations and experiments we've explored together today. Here at TheLazyCosmos, we've journeyed through the realms of theoretical physics, grappling with relativity, wormholes, and quantum paradoxes. But the real intrigue of time travel often lies not in formulas, but in strange stories, objects, and events scattered across human history. In this part, we delve into the realm of historical anomalies and alleged evidence for time travel, artifacts out of place and time, uncanny knowledge, and people whose origins seem shrouded in impossibility. As we sift through mysteries both famous and obscure, the question confronts us again and again. Do these tales truly hint at temporal visitors, or are they the result of coincidence, misinterpretation, or the relentless creativity of the human mind? Let's start with the concept of out-of-place artifacts, parts, objects that appear, by conventional understanding, to be far ahead of their time. The name was coined by Ivan T. Sanderson in the mid-20th century as he cataloged and classified seemingly anomalous archaeological finds. These artifacts are not merely curiosities. For some, they pose direct challenges to the established timeline of human technological progress. Consider the Antikythera mechanism, discovered off the Greek island of Antikythera in 1901 among the wreckage of a Roman cargo ship. For decades, the corroded gears and dials were underestimated as some strange navigational tool or celestial model. Only with the advent of modern radiography did researchers realize the full extent of the device's sophistication. It's a 2nd century BCE analog computer, capable of predicting eclipses and planetary motions with astonishing accuracy. Its complexity would not be equaled for another 1,000 years, until the gears of medieval European clocks began to turn. How could such technology spring forth and seemingly vanish for generations before resurfacing? Some enthusiasts see in the Antikythera mechanism the subtle footprint of lost knowledge, perhaps carried across time, though mainstream historians favor explanations rooted in forgotten genius and the quirks of history. Still, the mechanism stands as a powerful emblem of puzzling advancement, causing many to ask whether the past is as isolated from the future as it seems. Another classic part is the Baghdad battery, a set of ceramic jars with copper and iron rods, dating to ancient Mesopotamia, possibly as far back as 200 BCE. Some researchers speculate they functioned as primitive batteries, capable of generating a modest electric current when filled with vinegar or other acid. while skeptics argue that if they were batteries, there's little evidence of how or for what purpose these devices were used. The notion of electrical technology in the ancient world continues to generate debate and, at times, wild speculation about technological time travel. Moving from objects to knowledge, let's examine ancient texts and prophecies that appear uncannily prescient. The writings of Leonardo da Vinci, perhaps, humanity's archetypal polymath, burst with drawings and inventions seemingly out of step with his era. Flying machines, tanks, mechanical calculators, and scuba gear, all centuries ahead of their time. Critics point out that his designs were not fully functional, but the sheer scope of his imagination, paired with his anatomical studies rivaling those done in the 19th century, raises perennial questions. Was Da Vinci a visionary, a genius, or somehow the recipient of future knowledge? Some conspiracy theorists and speculative fiction writers have even suggested Da Vinci was guided by temporal visitors or was one himself, though there is no substantive evidence for these claims. A similar enigma surrounds Nostradamus, the 16th century French seer whose cryptic prophecies appear, depending on interpretation, to anticipate everything from the rise of Adolf Hitler to the 9/11 attacks. Skeptics rightly argue that Nostradamus wrote in vague, poetic language, making it easy for readers to retroactively impose meaning after the events occur. Yet, the volume and apparent specificity of his predictions remain a source of fascination. Is his work the product of acute historical insight, a clever manipulation of language, or could it be evidence, however slim, of information trickling in from the future? The question becomes even more pointed with the arrival of the John Titor affair in early Internet lore. Between 2000 and 2001, an anonymous poster on Internet forums claimed to be a U.S. government soldier from the year 2036, sent to retrieve an IBM 5100 computer as part of a mission to save future software systems. Titor's posts were not mere eccentric ramblings. They included technical details about the IBM 5100's undocumented capabilities that impressed some computer historians. He discussed the physics of time travel, referencing the then esoteric concept of microsingularities and explaining the operation of a temporal displacement unit built by GE in his future. Titor's most dramatic claims were about world events, the outbreak of civil war in the United States, nuclear exchanges, and the breakdown of global order. These events did not transpire as predicted, casting doubt on his story. Yet, in hindsight, Titor's descriptions of increasing political polarization, election controversies, and civil unrest resonated with real events from the late 2000s and 10s and early 2000s and 20s. Was this foresight, luck, social psychology, or something else? To add to the mystery, Titor vanished from the forums, explaining that his timeline would soon diverge from ours, and that his very existence in our world was uncertain. Debunkers have identified likely hoax suspects, but the detailed knowledge displayed by whoever was behind the posts remains a topic of debate. The Titor saga exemplifies the difficulties inherent in historical time travel evidence. Predictions that fail to materialize are quickly dismissed, while those that match real events are often declared retroactive interpretations or lucky guesses. The Titor affair underscores both the allure and the slippery nature of evidence, especially in an age where anyone can claim a fantastical provenance online. Even so, the case remains one of the most meticulously documented and debated time travel claims in internet culture. Let's turn now to visual anomalies, photographs or paintings that seem to capture impossibly advanced objects or people. The time-traveling hipster is a famous example. A 1940s photo from the reopening of a Canadian bridge appears to show a man dressed far more like someone from the early 2000s, sporting sunglasses and attire decades ahead of his time. Skeptics quickly tracked down analogs for all the garments and accessories he wore, some of which were indeed available, though unusual at the time. The image, however, went viral, feeding the imagination of those enthralled by the concept of photographic time travelers. Similarly, old paintings or films sometimes surface with curious details. A wristwatch in a 16th century portrait, a mobile phone-like object in ancient frescoes. Most are swiftly explained by fashion, artifacts, or objects whose design simply coincided, by chance, with later technology. Yet the recurrence of such anachronisms in art and imagery drives home our yearning for evidence of human minds that have transcended the ordinary flow of time. The stories extend beyond objects and images to people, individuals who appear in records seemingly without cause, or who possess knowledge impossible for their time. The legend of the Green Children of Woolpit, a pair of mysterious green-skinned children who appeared in the English village of Woolpit in the 12th century, has been cited as evidence for everything from space travel to parallel universes to time travel. The children spoke an unknown language, described a world largely underground, and eventually adapted to life in their new setting. Whether misunderstood foreigners, malnourished orphans, or examples of folklore misunderstood, the Woolpit children offer a classic case of a historical anomaly surrounded by speculation and myth. Other accounts reference unexplained disappearances and reappearances, people who seem to vanish without trace, only to appear years later unchanged, or whose origins simply cannot be traced to any known place or time. The story of Rudolph Fentz, often cited in time travel lore, tells of a man who purportedly appeared in New York in the 1950s, dressed in 19th century clothing and struck by a car moments after appearing. He carried coins and papers from the 1800s, and a subsequent investigation allegedly revealed he had vanished without a trace from his home in the preceding century. However, careful analysis shows that this tale likely originates from science fiction literature, not historical documentation. Yet its persistence highlights our fascination with sudden temporal crossings. Some cases are rooted in technological anachronism. The Dendra light, ancient Egyptian reliefs at the Temple of Dendra, depict what some claim resembles modern electric light bulbs or tubes. Egyptologists point to symbolic representations tied to mythology, but persistent claims arise in fringe circles, suggesting visitors from the future gifted technological knowledge to ancient civilizations. Maps and navigation. The 16th century Piri Reis map, drawn by the Ottoman admiral of the same name, appears to depict South America and Antarctic coasts with surprising accuracy. Some have interpreted this as evidence of lost or advanced geographical knowledge, possibly stemming from sources unknown to Piri Reis himself. The mainstream explanation attributes it to the collation of older maps and exaggerated speculation. Yet the case is cited repeatedly in time travel discussions. Beyond the physical, prophetic individuals repeatedly crop up across history and legend. Mark Twain, known for his wit and skepticism, reportedly predicted his own death in connection with Halley's Comet. He was born soon after Halley's passage in 1835 and died shortly after its return in 1910. He himself wrote, "The Almighty has said, no doubt, now here are these two unaccountable freaks. They came in together. They must go out together." Though easily painted as a coincidence, it is emblematic of human attempts to find meaning and pattern in the tapestry of time's passage. We must also consider the history of science itself, filled with instances where inventions, concepts, or theories suddenly leap ahead of their time. Take Nikola Tesla. His predictions outlining wireless communication, global information sharing, and the use of miniature devices conveniently portable for use in the hand. In a 1926 interview, he described a wireless system connecting people with a device which will fit in your vest pocket, eerily reminiscent of smartphones and the internet. Was Tesla a visionary perched on the edge of inevitability, or did his knowledge somehow transcend his era? Mainstream historians attribute his insight to the logical extension of radio and electrical theory, but the specificity of some forecasts continues to stun. Similarly, Jules Verne, writing in the 19th century, conjured up descriptions of submarines, video conferencing, and lunar travel long before their real-world manifestation. The genre of speculative fiction often anticipated technological revolutions, a testament to imagination's power, but also, perhaps, to uncanny intuition or undisclosed information. As we seek stronger evidence, our attention turns to the practice of remote viewing and psychic research, particularly during the Cold War. Declassified CIA documents reveal that U.S. intelligence agencies funded Stargate project experiments evaluating claims of psychic ability, including precognition, the ability to perceive future events. The results, as expected, were inconclusive and controversial, yet the resources devoted indicate serious attention to the possibility that information could, in some way, be transferred from the future to the present. Does any of this amount to scientific evidence for time travel? Strictly speaking, the answer is no. No case so far has withstood the crucible of repeatable experiment and critical review. The stories, images, objects, and individuals discussed above tantalize but never quite cross the threshold from legend to empirically supported fact. Yet the very persistence of these historical anomalies inspires ongoing investigation. Scientists such as Dr. Robert Nemiroff have conducted systematic studies for evidence of time travelers, looking for prescient information online, social media posts, or internet forums predicting major events with uncanny accuracy without plausible explanation. While no concrete evidence has emerged from these studies, they set important precedents for the kind of rigorous, data-driven searches that future researchers may pursue as technology advances. Modern-day technology itself adds new wrinkles to the puzzle. Today, algorithms can sift through immense data sets much faster than any human could, searching for patterns and anomalies that might escape detection. Patent databases hold thousands of inventions, some so far in advance of current capabilities that their existence feels uncanny. Advances in artificial intelligence and deep learning dramatically increase our ability to detect information out of time. That said, the most spectacular discoveries are often hoaxes, misunderstandings, or the result of processes that, while anomalous, remain within the bounds of normal causality. As we analyze historical anomalies and claim time travel evidence, several recurring themes deserve note. 1. Retroactive interpretation. Many claimed instances of prophecy or anomalous knowledge are only recognized as such after an event has occurred, enabling broad interpretation. This retrofitting is a classic cognitive bias and an ever-present risk in the study of historical claims. 2. Lost knowledge and forgotten genius. Human civilization's history is punctuated by periods when knowledge advances, then recedes. The apparent leaps in technology or understanding may mark the persistence of localized innovation, lost in the fog of time, then rediscovered centuries later. 3. The spread of folklore and urban mythology, stories about time travelers, anachronistic artifacts, and phenomenal predictions spread rapidly, increasingly so in the digital age. This unchecked proliferation means that even well-debunked cases can take on new life, with facts twisted, exaggerated, or outright manufactured. The impact of science fiction, literary, and cinematic works often lay the groundwork for later time travel claims. H.G. Wells's The Time Machine shaped cultural understanding of temporal journeys. Since then, time travel has become a central theme across all media, blurring the line between imaginative fiction and supposed evidence. 5. Psychological pattern. Recognition? Humans are built to detect pattern and meaning, sometimes where none exists. As a result, we often see causality, intent, or design in what may be random or coincidental. The phenomenon of apophenia, seeing connections in unrelated things, richly colors the time travel debate. 6. Evolving scientific paradigms. New advances in cosmology, quantum mechanics, and information theory suggest ways that the flow of time might not be as rigid as previously believed. The implications of delayed choice experiments, quantum entanglement, and multiverse theory open up possibilities for real-time transfer or translation across timelines, challenging our understanding of historical causality. If time travelers exist, if information or objects truly have crossed the barrier between eras, the evidence to date is almost excruciatingly subtle, hidden within anomalies, mysteries, and ambiguities. There is no artifact marked from the future, no living witness of time's violation who can be universally assessed and confirmed. That said, the debate persists, precisely because of the allure of these historical puzzles and the profound human compulsion to wonder if we have truly understood everything about our place and moment in the cosmos. So, where does this leave us on the lazy cosmos? As we scrutinize historical anomalies, devices ahead of their time, knowledge surpassing expectation, prophecies fulfilled against the odds, and people whose origins defy explanation, we become part of a process older than humanity itself. The quest to decipher the true nature of time and to understand whether its river can, in brief moments, be crossed in ways science only now begins to comprehend. We cannot, as responsible investigators, claim these historical anomalies as definitive proof for time travel. But we also cannot dismiss the pervasive sense that our neatly defined timelines have, on occasion, been disturbed in ways that beg for explanation. Every find, every legend, every enduring mystery is a puzzle piece, perhaps of time's grander tapestry, perhaps of the human imagination itself. The journey to uncover the truth pushes us ever forward. The next step is to examine scientific investigations born in our era, the experiments, projects, and revelations that continue to test the boundary between past, present, and future. It is here, at the intersection of anomaly and evidence, that the possibility of time travel remains most alive and where the lazy cosmos continues its tireless exploration. Having traversed the speculative landscape of historical anomalies and legendary tales, we now step into the realm of modern science, where theoretical possibility meets empirical investigation. While time travel remains elusive on a practical level, some of the world's leading labs, experiments, and government projects are exploring phenomena at the edge of what we know about time, causality, and reality itself. Welcome to the fourth act of our exploration, modern scientific investigations. The story of contemporary time travel research is rooted in the extraordinary advances of the 20th and 21st century physics. Our age has been marked by monumental discoveries and unprecedented technological leaps, a time when the wildest speculation can be mapped onto physical models, tested in particle accelerators, interrogated by quantum mechanics, and even weighed, in some cases, by governmental fact-finders. Let's begin with the Large Hadron Collider, LHC, at CERN in Switzerland, the most powerful particle accelerator ever built. It's a sprawling machine, 27 kilometers in circumference, designed to smash protons together at energies previously found only in the earliest moments of the universe. Physicists use the LHC to probe the nature of matter itself, to search for particles and forces that might reveal new dimensions, refine the standard model, and, as some hope, uncover loopholes in causality. In its pursuit of understanding, the LHC goes beyond the hunt for exotic particles like the Higgs boson. Some theorists suggest the collider might accidentally produce micro-black holes, tiny singularities whose brief existence might open the door to space-time anomalies. In 2014, CERN's theoretical teams actively debated whether these fleeting black holes could be linked to extra dimensions, postulated by string theory. If so, these extra dimensions might contain shortcuts, or wormholes, which could connect one point in spacetime to another, perhaps even facilitate time travel on subatomic scales. Though no evidence for stable wormholes or time-transcending micro-black holes has been found, the experiments raise profound questions. What happens, for example, if a particle travels through a wormhole and returns to a point in its own past? Would the laws of causality survive? While most physicists remain skeptical, the very act of posing the question within a rigorous scientific context is a testament to how far our understanding has advanced. Moving next to the world of quantum mechanics, we encounter phenomena that blur the boundaries of space, time, and causality. At the quantum scale, the neat progression from cause to effect erodes. Particles leap, states superpose, and realities seem, at times, to overlap and diverge. One of the key quantum experiments relevant to time travel is the delayed choice quantum eraser. Building on the work of John Wheeler, researchers set up arrangements where the path of a particle, like a photon, seems to be retroactively determined by measurements made after it has passed a critical juncture. You send a photon through a beam splitter only after it should have already registered as one outcome or another is a decision made that affects whether its past seems to have been a wave or a particle. In effect, the outcome appears to travel backward in time, as if the present measurement rewrites history. While most quantum physicists caution that these effects do not constitute true time travel, that is, transport of matter or causally connected information, they nonetheless suggest that the arrow of time at the quantum level is not absolute. The future and past are not always fixed, and experiments demonstrate that nature allows for a loophole in our classical intuition about history and prediction. Another quantum avenue is the phenomenon of entanglement. When two particles become entangled, their properties remain linked no matter how far apart they are in space, or, theoretically, in time. Some experiments have demonstrated entanglement swapping, where an uncoupled particle becomes entangled with another far removed in time, suggesting that quantum states can transcend the boundaries of the present moment. Could quantum entanglement ever form the basis for communication across time, perhaps even for future discoveries about temporal navigation? The answer remains unclear, but research continues at leading laboratories. Quantum physics also inspires more esoteric theories. The many worlds interpretation, introduced by Hugh Everett in the 1950s, proposes that every quantum event brings about a split in reality. Each possibility becomes a new universe. In this model, time travel paradoxes, like the grandfather paradox, are resolved. Every action that might interfere with your past simply branches the universe into a new timeline, preventing logical contradiction. This multiverse thinking has sparked speculation in physics, computer science, and philosophy, raising the question of whether scientific research might, one day, intentionally or unintentionally, touch upon the building blocks of alternate timelines. Alongside these experiments, time crystals, a new phase of matter discovered in the last decade, offer even stranger possibilities. Time crystals oscillate in a regular pattern, not just in space, but across time, seemingly defying the usual rules of thermal equilibrium. Scientists at Yale and Google have built and observed these crystals in the lab. And while no credible connection to macroscopic time travel has been found, their discovery hints that time structure and symmetry might be much richer than previously thought. Let's turn to theoretical constructs like the Alcubierre warp drive. In 1994, physicist Miguel Alcubierre derived a solution from Einstein's equations, allowing a spacecraft to contract space-time in front and expand it behind, potentially enabling travel faster than light. This warp bubble, if ever feasible, could make a journey of hundreds of light years in minutes or hours. Critics quickly pointed out that immense amounts of exotic negative energy would be required. But if such a drive could be engineered, relativity predicts it would create closed timelike curves, allowing for time travel as a consequence of faster-than-light navigation. Alcubierre's solution has become a serious touchstone in scientific labs and theoretical circles, especially as astronomers search for signs of advanced engineering elsewhere in the universe. While the energy requirements remain daunting, the idea continues to stimulate research into the nature of exotic matter and quantum fields. The embrace of wormhole theory remains strong. Kip Thorne, whose work is celebrated both in academia and popular culture, has analytically explored the possibility of traversable wormholes stabilized by negative energy. Thorne's calculations and the resulting literature establish clear protocols by which, if such matter could exist, wormholes could be used as time machines. The search for real-world evidence of traversable wormholes is ongoing. Astronomers study cosmic phenomena, gravitational waves, and high-energy particle collisions for any sign, but the search has so far been without clear result. Modern studies of closed timelike curves are conducted with quantum computers and logic circuits. David Deutsch, one of the fathers of quantum computation, has simulated the behavior of quantum systems under conditions where time loops exist. These studies demonstrate that information and causality can evolve in logically self-consistent ways, even in the presence of time loops, a remarkable result that validates some of the oldest paradox-defying hypotheses in relativistic physics. On Earth, temporal anomalies also appear in unexpected places. Some research in geology and paleontology focuses on dating methods, radiocarbon, uranium-thorium, and more. Occasionally, scientists encounter fossils or objects whose dates seem wildly discordant with established timelines. Most are due to contamination, methodological error, or natural processes. But every new technology in dating refines our understanding of time's passage. The pursuit is not limited to laboratories. Scientific curiosity has led to collaboration and controversy within government and military projects. The most widely debated example is the Philadelphia experiment, a legendary tale alleging that in 1943, the U.S. Navy achieved radar invisibility for the USS Eldridge, accidentally causing it to disappear and reappear several hundred miles away. Some accounts claim the sailors were physically shifted in time. Decades of investigation reveal the story likely originated from fiction and hearsay, with no credible scientific foundation. But the very persistence of such tales led to real U.S. government reviews. Similarly, the Montauk Project, an alleged series of experiments at Camp Hero in New York, supposedly sought to manipulate time, opening portals and sending people and equipment to other ages. The project is almost certainly a fabrication, emerging from a complex stew of declassified Cold War experiments and fictionalized accounts. Yet it left an enduring mark on popular consciousness and inspired generations to contemplate the intersection of military research and temporal mechanics. Less sensational, but more rigorously documented, are the hundreds of declassified CIA and Soviet Union files investigating remote viewing, psychic phenomena, and precognition. The Stargate project, carried out from the 1970s to the 1990s, evaluated the possibility of precognitive ability for intelligence purposes. While the results were inconclusive and the program ended, its existence demonstrates earnest interest at the highest levels in the possibility of accessing future information. Beyond legends and rumors, serious physicists have ventured into time travel research with increasing frequency. In 2013, astronomers Robert Nemiroff and Teresa Wilson systematically searched for prescient messages on social media and internet forums, specifically for posts that could only have been written with knowledge of future events. This project leveraged the rise of big data. Using precisely defined criteria, Nemiroff and Wilson evaluated thousands of posts for evidence of future leaks. No definite time traveler was found, but their methodology laid the foundation for future projects using artificial intelligence and pattern recognition. Other explorations have considered subatomic anomalies, particles that behave contrary to expectations, decay in unusual patterns, or move in ways that seem to suggest shortcuts through space-time. At Fermilab, SLAC, and other particle research centers, experiments continue to probe neutrino oscillations, high-energy cosmic rays, and the behavior of virtual particles, a shadowy quantum realm where, it is theorized, time itself may become fragmented or nonlinear. In cosmology, the search for cosmic strings, infinitely long, narrow defects in space-time, has gained urgency. Some models suggest that the intersection of two cosmic strings moving near the speed of light could create closed timelike curves. If these objects can be found or artificially generated, it might be possible to send signals, or matter, into the past. Observational studies using gravitational wave detection and cosmic background mapping are ongoing, and the discovery of such structures would be paradigm-shifting not only for time travel, but for understanding the very fabric of the universe. Astronomical observations also play a role. Some researchers have scoured historical data for astrophysical evidence of time anomalies, bursts of gamma rays or gravitational waves that defy conventional models or appear to repeat with impossible regularity. These signals, if found, might mark the intersection of cosmics, events, or even causality loops formed by time travelers at galactic scales. Furthermore, advances in chronobiology, the study of biological clocks, reveal that life itself responds to time in intricate, adaptive ways. Organisms have circadian rhythms, but some researchers investigate whether there are subtler, longer-term cycles influencing growth, aging, and species evolution. Could there be biological signatures of time travel, particularly among species or individuals exposed to extreme environments or physical conditions? Research is ongoing, and the answers may provide further clues as to how time navigation would impact life. Information theory is a new frontier, as scientists model the universe as a vast computational system. Seth Lloyd, a quantum physicist, has theorized that the universe itself is a quantum computer, and if so, it might accommodate calculations or processes from one register of time to another. If the universe is truly a computational system, perhaps time travel is simply a matter of accessing data at a different address, a transformation of indices within the cosmic code. Perhaps most tantalizing are the efforts among physicists to develop a theory of quantum gravity, uniting general relativity and quantum mechanics. This holy grail of physics would provide the rules governing not only the geometry of space-time, but also the probabilistic tapestry of quantum events. Early attempts at string theory, loop quantum gravity, and emergent space-time models seek to resolve whether space-time is continuous or granular, and whether causality is truly fundamental or an emergent property that can be bent, stretched, or even violated under rare circumstances. The advances in computational physics, particularly simulating closed timelike curves and alternate timelines, have produced surprising results. Quantum computers can model paradox-resistant algorithms, data exchange across simulated time loops, and bootstrap causal loops where an event appears to have no origin except the loop itself. As quantum computers grow in power, they may one day provide experimental evidence for models of time travel once thought purely speculative. In parallel, private initiatives and amateur investigations proliferate. Citizen scientists search patent records for inventions out of their time, scan historical archives for unsolved mysteries, and use statistical analysis to evaluate predictive data unusual enough to warrant further study. Online collaborative efforts, like open-source AI programs, now have the ability to sift through vast records in search of prescient information, anomalous technological references, or unexplained events. Despite these advances, every credible contemporary investigation faces enormous challenges. The difference between possible and practical is immense in physics. While equations and models may permit time travel, engineering a device capable of traversing the timeline without catastrophic side effects, destruction by radiation, paradox-driven instability, or quantum feedback remains a distant dream. Further, the chronology protection conjecture by Stephen Hawking remains a central caution. Hawking theorized, based on quantum feedback loops that any attempt to construct a time machine would trigger immense energy feedback, destroying the apparatus and preserving causality. This conjecture has not been disproven, and many physicists regard it as a likely constraint on macroscopic time travel. However, the relentless curiosity of science cannot be subdued. Each year, conferences and journals feature new papers on temporal mechanics, quantum causality, and experimental approaches to space-time anomalies. The search for loopholes, the refinement of measurement, and the cross-disciplinary embrace of time's mysteries ensure that investigation continues. It's worth noting, too, the meta-scientific aspect, the sociology and psychology of time travel research. Many scientists pursue time travel from a standpoint of pure curiosity or as a testbed for models of reality's deepest boundaries. Indeed, the investigation of time's arrow, causality, and paradox sits at the crossroads of physics, mathematics, philosophy, and information theory. The scientific method itself can be seen as a form of time navigation, moving knowledge from hypothesis to test, prediction to confirmation, the unknown to the known. In summary, modern scientific investigations, whether in the collider tunnels of Switzerland, the quantum labs of California, the computational centers of MIT, or the observational systems of deep space telescopes, continue to probe the mysteries of time travel. They confront formidable barriers, but also uncover astonishing hints that the universe may be richer, more flexible, and stranger than we currently understand. While no experiment has yet produced a working time machine, and no project has definitively proved a signal from the future, the progress of modern science means that time travel is no longer a purely fictional conceit. It is a question under active study by some of the brightest minds on the planet. A question whose answer may yet rewrite our understanding not only of time, but of existence itself. For the community of the Lazy Cosmos, this should be a profound encouragement. We are living at an age when the once impossible is now within reach, when the intersection of theory and experiment propels us towards the very brink of unimaginable possibility. The boundary between today and tomorrow, present and future, is being explored with every new discovery, every experiment, and every act of curiosity. As science edges forward, the prospect of time travel remains, if not inevitable, then at least endlessly enticing. The only question is, how long until the mysteries of time yield their secrets, and we find ourselves voyaging, at last, along the hidden currents of the timeline itself? As we've seen, the theoretical foundations for time travel exist. Historical anomalies tantalize us with possibilities, and modern scientific investigations push the boundaries of what we thought possible. But if time travelers are truly among us, how would we detect them? What would constitute genuine evidence? And perhaps, most importantly, what systematic methods could we employ to separate authentic temporal anomalies from coincidence, misinterpretation, or deliberate deception? Welcome to Part 5 of our investigation, the search for evidence. The challenge of detecting time travelers is fundamentally different from other scientific pursuits. We're not looking for a new particle that leaves traces in a detector, or a distant galaxy that emits predictable wavelengths of light. We're searching for intelligence, conscious beings who, if they exist, would likely be sophisticated enough to avoid detection. This creates what researchers call an adversarial search problem, where the very subjects we're trying to find have both the motivation and the capability to remain hidden. The methodological framework. The most rigorous approach to this search was pioneered by Dr. Robert Nemiroff at Michigan Technological University. In 2013, Nemiroff and his colleague Teresa Wilson published the first peer-reviewed scientific paper specifically designed to search for time travelers using empirical methods. Their approach was elegantly simple. If time travelers from the future are present in our time, they might possess knowledge of future events that hasn't yet occurred from our perspective. Nemiroff's team searched the internet for what they termed prescient information, specific details about events posted online before those events actually happened. They focused on two major criteria. The information had to be specific enough that it couldn't be explained by educated guessing, and it had to be posted with timestamps that precede the events in question. Their search covered major events like the election of Pope Francis and the discovery of Comet Ison, looking for mentions of these specific names or details before they were publicly known. The methodology was sound, but the results were disappointing from a time travel perspective. No definitive evidence of prescient knowledge was found. However, Nemiroff's work established crucial precedents for how such searches should be conducted. The key insight was that in our digital age, time travelers would leave digital footprints that could be systematically analyzed. Building on this foundation, modern searches have become far more sophisticated. Today's artificial intelligence systems can process millions of social media posts, forum discussions, patent applications, and archived communications looking for patterns that human researchers would miss. Machine learning algorithms can identify linguistic anachronisms, words, phrases, or concepts that appear before they should exist. They can detect knowledge clusters where individuals demonstrate understanding of technologies, events, or discoveries years before they become public knowledge. What to look for? Technological anachronisms. One of the most promising avenues for detecting time travelers involves identifying technological knowledge that appears out of time. Consider how a time traveler might inadvertently reveal their origins. They might describe future technologies in casual conversation, file patents that are decades ahead of current capabilities, or make investment decisions based on knowledge of technological developments that haven't yet occurred. Patent databases represent a particularly rich hunting ground. The U.S. Patent and Trademark Office contains millions of applications dating back centuries. Some researchers have developed algorithms to scan these databases, looking for inventions that seem impossibly advanced for their time period. The challenge lies in distinguishing genuine anachronisms from the work of visionary inventors who were simply ahead of their contemporaries. Take, for example, the work of Nikola Tesla, whose patents and writings describe technologies that wouldn't be fully realized until decades after his death. Tesla wrote about wireless power transmission, global communication networks, and devices that sound remarkably similar to modern smartphones and the Internet. In a 1926 interview with Collier's magazine, Tesla described a world where we shall be able to communicate with one another instantly, irrespective of distance, using devices that would fit in our vest pocket. He envisioned a global system where a businessman in New York will dictate instructions and they will instantly appear in type at his office in London or elsewhere. This description, written in 1926, is essentially a perfect description of email and mobile internet access. Was Tesla a visionary genius, or did he possess knowledge from the future? The question becomes more intriguing when we consider that some of Tesla's technical descriptions included details about the infrastructure required for these technologies, details that wouldn't be understood until the development of satellite networks and fiber optic communications decades later. Modern patent analysis uses natural language processing to identify descriptions of technologies that reference concepts, materials, or processes not yet discovered or named. For instance, a patent filed in the 1960s that casually mentions carbon nanotubes or quantum entanglement might warrant investigation, since these terms weren't coined until much later. Investment patterns and market prescience financial markets offer another avenue for detecting temporal anomalies. If time travelers were present in our era, some might use their knowledge of future events to make investments or trades that would seem impossibly prescient to contemporary observers. The challenge is distinguishing this from legitimate market analysis, insider trading, or simple luck. Researchers have developed algorithms to scan historical trading data, looking for patterns that exceed normal statistical boundaries. They search for investors who consistently made profitable decisions based on information that shouldn't have been available at the time. The system looks for individuals who repeatedly bet against seemingly strong companies just before major scandals broke, or who invested heavily in obscure technologies just before breakthrough discoveries made them valuable. One intriguing case involves an anonymous trader who, in the weeks before September 11th, 2001, placed unusually large bets against airline stocks. The trades were so unusual that they triggered immediate FBI investigations. While the investigations concluded that the trades were likely coincidental or based on insider knowledge unrelated to the attacks, the case demonstrates how modern surveillance systems might detect temporal anomalies if they existed. More recently, researchers have identified individuals who seem to have an uncanny ability to predict cryptocurrency market movements, technological breakthrough announcements, or geopolitical events with accuracy that defies statistical explanation. While most can be attributed to sophisticated analysis or privileged information, a small percentage remain unexplained and continue to be monitored. Linguistic and cultural anachronisms language evolves constantly, and each era has its distinctive vocabulary, idioms, and cultural references. A time traveler might inadvertently reveal their temporal origins through linguistic slips, using phrases that haven't been invented yet, referencing cultural events from their future, or demonstrating familiarity with social concepts that don't yet exist in our time. Advanced natural language processing systems now scan historical documents, recorded conversations, and written correspondence looking for these linguistic anachronisms. The systems have been trained on vast databases of historical language use, allowing them to identify when someone uses words, phrases, or concepts before they appeared in the historical record. For example, the phrase online, in its modern computer-related sense, didn't appear until the 1960s, so finding this usage in documents dated earlier would be significant. Similarly, references to DNA before Watson and Crick's 1953 discovery, or casual mentions of black holes before John Wheeler coined the term in 1967, might indicate temporal displacement. The challenge is immense because language evolution is complex and poorly documented in many cases. Regional dialects, professional jargon, and subculture terminology can create false positives. Moreover, sophisticated time travelers would likely study the language patterns of their target era to avoid such mistakes. Behavioral pattern analysis. Beyond specific knowledge or linguistic clues, time travelers might reveal themselves through behavioral patterns that don't quite fit their supposed era. Modern surveillance and data analysis systems can identify individuals whose behavior patterns seem anomalous for their time period. This might include consumption patterns that don't match contemporary norms, social behaviors that seem ahead of their time, or decision-making processes that reflect future knowledge. For instance, someone in the 1950s who consistently avoided products later found to be carcinogenic, or who made lifestyle choices that aligned perfectly with future health recommendations, might warrant investigation. Researchers have developed psychological profiles of what time travelers might look like behaviorally. They might demonstrate unusual risk assessment abilities, make decisions that seem irrational in contemporary context but prove prescient over time, or show knowledge of historical patterns that allows them to anticipate social and political developments with unusual accuracy. The John Titor Case Study, a detailed analysis. The most thoroughly documented case of alleged time travel remains the John Titor affair, which provides an excellent case study for modern evidence evaluation methods. Between November 2000 and March 2001, an individual claiming to be a time traveler from 2036 posted detailed messages on internet forums, particularly Time Travel Institute and various bulletin board systems. What made Titor's case unique was the specificity of his claims and the technical detail he provided. Unlike vague prophecies or general predictions, Titor offered precise technical specifications for his time travel device, detailed explanations of the physics involved, and specific predictions about future events with exact dates and circumstances. Modern analysis of the Titor posts reveals several intriguing elements. His description of time travel physics, while not entirely accurate by current understanding, demonstrated sophisticated knowledge of concepts that were cutting edge in theoretical physics at the time. He discussed micro-singularities, Kerr black holes, and closed timelike curves, concepts that were largely confined to academic physics journals. More significantly, Titor provided detailed specifications for his alleged time machine, including technical drawings and operational procedures. He claimed the device was manufactured by General Electric in 2034 and used dual microsingularities contained within a magnetic field to create closed timelike curves. While the physics is questionable, the level of technical detail suggests either extensive knowledge of theoretical physics or possibly genuine future knowledge. Titor's predictions offer another avenue for analysis. He predicted an American Civil War beginning around 2005, escalating through 2008, and culminating in 2015. While these specific events didn't occur as described, researchers have noted that Titor's descriptions of increasing political polarization, constitutional crises, and social unrest bear striking resemblances to actual events from 2016 through 2024. Modern artificial intelligence analysis of Titor's writing style, technical knowledge, and predictive accuracy continues to yield intriguing results. Linguistic analysis suggests the posts were written by someone with advanced education in physics or engineering. Predictive analysis shows that while specific events didn't match his timeline, broader social and technological trends aligned with his descriptions more often than statistical chance would suggest. Digital archaeology and historical searches. The digital age has created unprecedented opportunities for evidence detection, through what researchers call digital archaeology. Every email, social media post, forum discussion, and online interaction leaves permanent traces that can be analyzed for temporal anomalies. Modern search algorithms can process terabytes of historical digital data looking for patterns that suggest prescient knowledge. They can identify individuals who consistently demonstrated knowledge of future events, technologies, or discoveries before they became public. The systems can track the spread of information through digital networks to identify instances where knowledge appeared to originate from unknown sources. One promising approach involves analyzing the timing and content of domain name registrations. If time travelers were establishing digital presences in our era, they might register domain names related to future companies, technologies, or events years before these become relevant. Researchers have identified several cases where domain names were registered years before the associated companies were founded or technologies were announced, though most can be explained by speculation or trademark protection. Social media platforms provide another rich source of data. Researchers can analyze the entire history of posts, comments, and interactions looking for users who consistently demonstrate unusual prescience about future events. The systems can identify users who seem to have advanced knowledge of natural disasters, political developments, or technological breakthroughs. Physical evidence and forensic analysis. While much modern searching focuses on digital evidence, physical artifacts remain important. Advanced forensic techniques can now detect materials, manufacturing processes, or design elements that are anachronistic for their supposed time period. Modern isotopic analysis can determine when materials were created with precision that would have been impossible just decades ago. Researchers can analyze the atomic composition of metals, plastics, and other materials to determine not just when they were made, but potentially where and using what processes. If time travelers brought physical objects from the future, these forensic techniques might detect them. Manufacturing analysis has become equally sophisticated. Modern production processes leave distinctive signatures, tool marks, material compositions, assembly techniques that are characteristic of specific time periods and technologies. An object that appears to be from the 1950s but shows manufacturing signatures consistent with modern automated production might indicate temporal displacement. The problem of sophisticated concealment. As detection methods become more sophisticated, we must also consider that time travelers would likely be equally sophisticated in their concealment efforts. Advanced civilizations capable of time travel would presumably understand the detection methods available in our era and take steps to avoid them. This creates an arms race between detection and concealment. As our search methods improve, time travelers would presumably adapt their concealment strategies. They might use period-appropriate materials and manufacturing processes, study historical language patterns to avoid linguistic anachronisms, and carefully limit their use of future knowledge to avoid creating detectable patterns. The most successful time travelers might be those who never reveal themselves at all, who observe without interfering, who gather information without leaving traces, who exist among us while maintaining perfect temporal camouflage. These individuals would be virtually impossible to detect using current methods. Collaborative networks and citizen science. The scale of the search for time travelers has led to the development of collaborative networks involving both professional researchers and citizen scientists. Online communities dedicated to temporal anomaly research have emerged, sharing data, methodologies, and findings across global networks. These collaborative efforts leverage the power of distributed computing and crowdsourced analysis. Thousands of individuals can simultaneously search different aspects of the historical record, analyze various data streams, and investigate promising leads. The approach has proven successful in other fields, from searching for extraterrestrial intelligence to discovering new astronomical objects, and shows promise for temporal research. Modern platforms allow researchers to share data sets, analytical tools, and findings in real time. Machine learning algorithms can be trained on data contributed by multiple researchers, improving their ability to detect subtle patterns that might indicate temporal anomalies. The significance of negative results. It's important to note that the absence of detected time travelers doesn't necessarily mean they don't exist. The search methods, while sophisticated, are limited by current technology and understanding. Moreover, truly advanced time travelers might be sophisticated enough to avoid all current detection methods. However, negative results are scientifically valuable. They help establish parameters for what kinds of time travel, if any, might be occurring. They rule out certain types of temporal interference and help refine our understanding of what to look for. The systematic search for time travelers also advances our understanding of information flow, predictive patterns, and anomaly detection more generally. The techniques developed for temporal research have applications in cybersecurity, market analysis, historical research, and other fields. Future directions. As artificial intelligence continues to advance, our ability to search for temporal anomalies will grow exponentially. Future AI systems may be able to process vast amounts of historical data with far greater sophistication than current systems allow. They may identify subtle patterns that current methods miss, or detect types of evidence we haven't yet learned to look for. Quantum computing may eventually allow us to simulate complex temporal scenarios, helping us understand what kinds of evidence different types of time travel might leave behind. As our theoretical understanding of time travel improves, we'll be better equipped to know what to search for. The search for evidence of time travelers represents a unique intersection of rigorous scientific methodology and speculative investigation. While we haven't yet found definitive proof of temporal visitors, the search itself pushes the boundaries of data analysis, pattern recognition, and anomaly detection. Whether or not time travelers walk among us, the quest to find them continues to advance our understanding of information, causality, and the nature of evidence itself. For the TheLazyCosmos community, this ongoing search represents humanity at its most curious and methodical, using every tool at our disposal to probe the deepest mysteries of existence. The evidence may remain elusive, but the search itself embodies the relentless human drive to understand our place in the vast, mysterious cosmos. As we draw nearer to the edges of what science dares to imagine, our quest inevitably intersects with one of the greatest intellectual puzzles of our age, the Fermi Paradox. Named for the brilliant physicist Enrico Fermi, this paradox presents a hauntingly simple question, possibly the single question most likely to reshape humanity's cosmic perspective. If the universe is so vast, so ancient, and so obviously habitable, then where is everybody? For the TheLazyCosmos, the Fermi Paradox is far more than an astrophysical curiosity. It is the gateway to contemplating not only alien life, but the nature of time itself and the silent mysteries that bind us to the present. In this segment, we'll trace the paradox from its historical roots, explore the most prominent solutions, and weave its implications into the strange tapestry of time travel. We'll examine whether our universe's apparent silence can be explained if the denizens of the cosmos aren't just hidden among the stars, but also spread across the rivers and tributaries of time. 1. The origins and enigma of the Fermi Paradox. The Fermi Paradox's genesis is famously informal. In the summer of 1950, while lunching with fellow physicists at Los Alamos, Enrico Fermi sketched out a simple calculation. Given the Milky Way's billions of stars, the galaxy's age, and the speed with which technological civilizations should, in principle, colonize the stars, Fermi concluded that even a modestly ambitious civilization could populate the galaxy in a few tens of millions of years, a blink compared to its 13.6 billion year lifespan. Someone remarked on a recent spate of flying saucer sightings, to which Fermi replied, "Where is everybody?" That offhand question ignited decades of scientific and philosophical debate. We now know with certainty that the universe is not just large, but unfathomably vast. The observable cosmos contains well over 2 trillion galaxies, each with hundreds of billions of stars, and, most likely, even more planets. Thanks to telescopes like Kepler and TESS, we routinely discover worlds within the habitable zones of their suns, zones where liquid water, and thus life, might thrive. Calculations, such as the Drake equation, tempt us with the suggestion that intelligent life should not only be possible, it should be common. Yet decades of dedicated searches, from SETI's radio arrays to laser pulse monitoring, have yielded only a profound silence. Second possible solutions: the universe's quietude. Over the years, thinkers have proposed scores of solutions, ranging from the mundane to the cosmic. Some posit the challenge of interstellar distances. Traveling from star to star is hard and expensive, requiring technology and resources that may simply remain out of reach. Others suggest life, though abundant at the microbial level, rarely climbs the evolutionary ladder to intelligence. The rare Earth hypothesis proposes that the combination of conditions sustaining advanced life is so fragile that we are, in effect, alone. There are great filter arguments hypothesizing that chemical, biological, or cultural catastrophes prevent civilizations from lasting long after they achieve technical sophistication. These filters might exist before intelligence, life is rare, or afterward, intelligence self-destructs. Diseases, warfare, resource depletion, climate disaster, or runaway artificial intelligence all have been posited as plausible limiting factors. Some argue we may simply not be listening at the right frequencies, epochs, or dimensions. Others posit stealth, the zoo hypothesis, suggesting that advanced life quietly observes us, perhaps out of ethical concern, curiosity, or some cosmic version of the prime directive. The dark forest theory, popularized by Liu Cixin's novel, imagines the galaxy as a lethal contest for survival, where silence is essential lest one's presence be revealed to hostile civilizations. Third time and the Fermi Paradox, the fourth dimension. Yet lurking beneath these solutions stands a further possibility, even more provocative as our investigation into time travel deepens. What if the answer to the Fermi Paradox is not spatial distance, but temporal distance? What if the civilizations that fill the cosmos do not all exist concurrently, but are spread across time's river in ways our senses cannot perceive. Let's consider the time scales. Earth has been habitable for almost 4 billion years. Advanced life, as we understand it, emerged only in the last half-billion. Humanity has built radio transmitters for barely a century. Our signals, traveling at light speed outward from Earth, now form a faint bubble 100 light-years wide against a background galaxy more than 100,000 light-years across. Other civilizations, if they exist, may have emerged millions or billions of years before or after ours. From this perspective, the likelihood that two civilizations' technological windows coincide is vanishingly small. Cosmic silence may simply reflect a time mismatch, not a lack of company. The odds of civilizations overlapping in their eras of detectability may be greatly outweighed by vast gaps of time between rises and falls. If time is a vast ocean, then intelligent life may be islands, each emerging for a few centuries or millennia before receding beneath cultural tides or cosmic catastrophe. And like isolated islands, they may never have the opportunity to see or reach each other, unless the laws of time itself allow for traversal of its depths and distances. Fourth, cosmic archaeology, detecting ancient civilizations across time. This raises a fascinating question. If civilizations lived among the stars millions or billions of years ago, could we ever detect their presence? Scientists are now exploring cosmic archaeology, trying to read the clues left behind by civilizations long vanished. Perhaps we could find evidence in the form of anomalous planetary atmospheres filled with engineered gases, ancient probes drifting through interstellar space, or macro-engineering projects like Dyson spheres, visible across the electromagnetic spectrum. Searches for techno-signatures now extend beyond radio waves to laser pulses, infrared excess, unusual planetary transits, and more. An ancient civilization might leave remnants in planetary isotopic ratios, unusual patterns in starlight, or artifacts scattered across a system. Some have even suggested that the WOW signal detected by SETI in 1977 could be the faint echo of a civilization whose technological window has already closed. But every search comes with a bias. We expect contemporaneity. We look for signals emitted now, that we receive now. What if messages are stored, not broadcast, recorded in asteroid belts, moons, or even in the deep digital structure of space itself, awaiting rediscovery by future species? Some theorists have suggested that cosmic signals could be encoded in the laws of physics, or that information could be stored within quantum states, a message not just from another place, but from another time. V. The prime directive and time travel, cosmic ethics. One solution to the Fermi Paradox is the possibility that advanced civilizations deliberately refrain from interference, guided by some version of the prime directive. In Star Trek's vision, advanced species agree to avoid contact with developing civilizations, allowing them to form without external influence. But suppose the prime directive operates not only spatially, but temporally. What if advanced civilizations, capable of traveling through time, avoid influencing past cultures to prevent paradox and preserve the integrity of cosmic history? The temporal prime directive, as posited in science fiction, would require time travelers to act as cosmic archaeologists, observing but never interfering, recording but never reshaping, ensuring that their presence leaves no mark on the timeline. This notion aligns with the zoo hypothesis, but extends it across the fourth dimension. We may be living in a well-protected temporal enclave, our timeline shielded from intervention, so that our civilization can develop according to its own principles, mistakes, and triumphs. Those with access to temporal navigation might exist only as silent observers, invisible precisely because cosmic ethics demand restraint. The butterfly effect and minimal intervention. Time travel, as our physics segments explored, introduces paradox. Most famously, the grandfather paradox and bootstrap paradox. Even a minimal change in the past could have unpredictable, cascading effects on the future. Edward Lorenz's butterfly effect, the observation that small changes in initial conditions produce dramatic future outcomes, becomes overwhelming at the level of cosmic history. Should time travelers exist and possess a strong understanding of chaos theory, their actions would be governed by a principle of extreme caution. The most careful time travelers would do nothing at all, leaving no evidence, making no intervention that might disrupt the development of civilizations. From this perspective, the silence demanded by the Fermi Paradox becomes a necessity for time travelers as well as alien visitors. Any signal intervention or direct contact risks catastrophic instability, not just of society, but of causality itself. 7. The multiverse and many worlds. Avoiding paradox. Quantum mechanics, with its many worlds interpretation, provides a framework for circumventing paradox. Each intervention in the past might spawn a new timeline, relegating causality to a web rather than a single linear thread. If time travelers operate within the multiverse, their interventions may create new universes, each distinct from the original. But if the goal is to preserve continuity, to avoid flooding the cosmos with infinite branching timelines, then minimal or non-existent intervention is again favored. For civilizations evolved enough to grasp these dangers, the likely default is silence, observation, and meticulous restraint. 8. The Fermi Paradox as a constraint upon time travel. Flip the question on its head. What if the very conditions that produce the Fermi Paradox are the same constraints that govern time travel? Perhaps civilizations capable of temporal navigation discover that the risks are too great and create cultural, technological, or even physical constraints to prevent time travel. Here, Stephen Hawking's chronology protection conjecture takes center stage. The universe may be self-protecting, quantum feedback destroying would-be time machines before they can function, or statistical physics enforcing the exclusion of temporal intervention. Perhaps the silence we observe is not only spatial but temporal, a natural firewall preventing civilizations from tampering with causality. If true, the answer to the Fermi Paradox is not that life is rare, but that survival requires discretion so absolute that even time itself is unbreachable. 9th, temporal steganography, hidden messages across time. If advanced civilizations wish to avoid detection, whether spatially or temporally, they may resort to techniques far subtler than radio broadcasts or visible megastructures. Temporal steganography, a process in which messages are hidden within the structure of physical reality, mathematics, or genetic codes, could allow civilizations to leave traces accessible only to similarly advanced cultures. Researchers have speculated that DNA, for example, may contain traces of cosmic signals, patterns or sequences too regular to be random. Perhaps a message from earlier epochs or distant cultures. Others look for mathematical constants, anomalous patterns in the cosmic microwave background, or strange regularities in the distribution of prime numbers. If temporal travelers are bound by rules of concealment They might hide their messages in structures meant to be discovered only when a civilization achieves the necessary level of maturity, understanding, or ethical development. The whispers from time may exist around us now, awaiting decipherment by our distant descendants. X. The role of machine intelligence and post-biological evolution. Our search for evidence must also reckon with the possibility that advanced civilizations rapidly evolve into machine intelligence. If conscious beings merge with computation, their capacity for time navigation, simulation, and concealment may multiply exponentially. Machine intelligence, unconstrained by biological imperatives, may regard temporal restraint and cosmic silence as default modes of interaction. For such entities, communication across galactic distances or centuries may be trivial, but their operational logic may remain inscrutable to us. Their evidence, signals, or interventions may be so subtle as to be undetectable or deliberately omitted to avoid influence. Perhaps the universe's silence conceals a vast culture of post-biological civilization living alongside us in the quantum substrate, or folded within dimensions unimagined. Time travel, then, is not only possible, but routine, yet so tightly regulated as to leave not a ripple upon the surface of history. 11th, cosmic isolation, deliberate or structural. Some theorists argue that cosmic isolation may be a deliberate choice or the inevitable result of the universe's structure. Civilizations may withdraw into simulation, preferring virtual realities to physical exploration. Douglas Adams famously joked that the reason we haven't heard from aliens is that they're too busy enjoying themselves virtualizing their cosmos. Alternatively, the laws of physics may ensure isolation by making time travel and long-distance communication expensive, dangerous, or impossible. Perhaps the universe is simply structured to protect nascent civilizations from outside interference, allowing independent development, discovery, and evolution. 12th, observational consequences. What would we see? If our silence stems from temporal separation or concealment, what would its consequences be? Could we find indirect evidence? A signature of time travel or cosmic ethics? We might observe unexplained anomalies, artifact patterns that don't fit known evolutionary trends, mathematical signatures in DNA, or mysterious missing signals in cosmic data. Our inability to detect contemporaneous civilizations might be itself a clue, a cosmic red flag indicating the presence of a powerful law of concealment. The hastily dismissed UFO signals, fast radio bursts, or unexplained quantum phenomena could, in this context, be the muffled echoes of civilizations forbidden or prevented from full contact. The challenge for us is recognizing these clues, the cosmic equivalent of footprints in deep snow, half erased but not wholly gone. 13th, from silence to invitation. Are we meant to join the conversation? Is it possible that cosmic silence is an invitation? A challenge for us to solve the great mysteries, to develop the tools, ethics, and understanding needed to join a universal culture operating across both space and time? Perhaps the Fermi Paradox is not a warning or despair, but the entry condition for a higher phase of existence. As we advance, our own capacity for both physical and temporal exploration grows. Artificial intelligence expands our vision. Theoretical advancements refine our understanding. Quantum computers and new physics may allow us, one day, to tiptoe across the rivers of time, joining the conversation that has spanned eons but remained just out of reach. The very process of searching, straining our senses to hear, reaching our minds to comprehend, building tools to detect, maybe preparing us for our eventual initiation into a collective that transcends era as well as distance. The intersection of time travel and cosmic community. Ultimately, the intersection between the Fermi Paradox and time travel offers a profound perspective on the human quest. Our loneliness in the universe is not a verdict, but a puzzle. Perhaps our destiny lies not in desperate search for spatial neighbors, but in the patient development of tools, understanding, and ethics that allow us, one day, to converse across the chasms of time. As our journey through the cosmos continues, science suggests that the ladder toward maturity has many rungs, and one is the ability to respect the silence, to master the tools of both detection and restraint. If the cosmic community exists, whether in the form of aliens or time travelers, it may weigh our worth not in technology, but in wisdom, the capacity to listen, to search, to ponder before we dare to speak. And in this vast silence, perhaps our greatest conversation is yet to come. So let's pause here amid the cosmic mystery. The Fermi Paradox asks us, where is everybody? But perhaps the question is also, when is everybody? As we've explored in this episode, the universe's silence may not be emptiness, but the echo of civilizations spread across unimaginable distances and epochs, guided by principles we can scarcely grasp. Time travel and cosmic ethics together counsel caution, curiosity, and humility. Whether the ultimate answer is solitude, concealed company, or a community yet to reveal itself, the paradox drives us to become not only explorers, but keen listeners in the cosmic dark. For all of us at the Lazy Cosmos, the search does not end with silence. It is only just beginning. The next step is ours, to think, to question, to search, and above all, to ask whether the timeline we inhabit is just one among many, echoing with possibilities as deep as the universe itself. If you've stayed with us this far, you're already a vital part of this search. Your curiosity, ideas, and questions fuel our ongoing investigation. So hit that subscribe button, ring the notification bell, and join the Lazy Cosmos community. Drop your thoughts in the comments. What's your preferred solution to the Fermi Paradox? Do you believe time travel might explain the silence, or is the answer hidden elsewhere? Share any anomalies, signals, or patterns you've encountered in your own cosmic wanderings. And if you're a time traveler or a seeker from another era, leave us a sign. Memory itself is the artifact of time. Every question you ask helps us chart this unknown territory together. Like, share, and subscribe for more cosmic investigations, deep dives, and the quantum mysteries just beyond the horizon. Until our next journey, keep listening to the silence, keep watching the stars, and remember, sometimes the loudest answers in the universe are hidden, not in sound, but in the profound, echoing quiet that binds us all across time. Stay curious. Stay cosmic. This is the Lazy Cosmos, and our adventure through space-time is only just beginning.